Okay, this is next lecture on invariant maximality, presumably lecture 36 on, yeah, by Harvey Friedman, please.
Thank you. So, yeah, I was intending to go beyond this chapter two as I promised, and something came up that is important expositionally. So, um, and now I'm in a state of flux because I'm adding some material that supports the proper presentation of this new idea, and that will also require that I talk about this next week. So we're still here. Okay, so what's happened is, if you recall, um, if you recall, what happened is that I even have this new chapter um, two because of the realization that the end shift was so natural. The end shift was so natural, and therefore I had an improved front end of this whole invariant maximality for the mathematical community, especially for the mathematical community, for everybody, but also especially for them. And so the end shift was so good that I created this new chapter surrounding the end shift and the use of Q and the intervals minus and n. Uh, if you recall, the other stuff, which has a little bit different direction and is also important, was only on the interval minus 1, 1, and use fractions and so forth. Um, so what happened is I suddenly realized that uh, the way I did the minus 1, 1 also suggests a thing called the pure end shift. The pure end shift uh, is weaker than the end shift, but the pure end shift, if you use the pure end shift, uh, it reverses just as well to the old reversal that that's been constant for a long time. The big reversal in the old chapter four, which is going to become the new chapter six. Um, so I have decided now, oh, and the point is that this pure end shift is even better, significantly, is even better than the end shift. The pure end shift is better than the end shift. So the leading statement is going to be a little bit weaker statement with a pure end shift. Also, the leading statement that I'm going to use most forcefully is on Q, not on the intervals. And the reason I do that is because it's sort of more natural to consider the thing on Q. Um, However, footnote, I don't know whether this statement is independent. I do know it's independent, however, when you do it on the intervals, minus n, then there's no problem. That's independent. That requires large cardinals. However, if you just do it on Q, I don't know. But then I don't care in terms of the presentation to the math community. So here's the story. Here's this theorem that's now as thrilling as I can make it, even more thrilling, whatever that means, than the original uh, uh, one with end shift, which is more thrilling than the ones on the interval minus 1, 1. More thrilling means you can more immediately absolutely see what it says and more immediately absolutely realize it's totally natural. Um, and uh, and so that what and so this has caused a reorganization and rethinking of the exposition of this, which has caused a reorganization and some additional work that has to be done. It's not major at all, but it's sufficiently time consuming, and I only came up with this idea clearly a few days ago that I certainly didn't complete it by today. There's another insight. So let me go through, and there's another insight that happened during this last week that is causing also this to be growing a little bit in size, and definitely needs next week lecture. So we'll get to that. First of all, I changed the title of the chapter two. It's now called. The reason I don't want to call it what I had before was, see, what I had before was the end shift and end invariance in maximality and an end invariant maximality, something like that. But now I have three different invariance notions that I use. The third one being this brand new pure end shift invariance. So there's three um, uh, independently important uh, invariants. The first one, the first one, which is the weakest one, weakest invariance, is the pure end-shift invariance, and that's the one that's most thrilling for the casual observer of this invariant maximality. Just somebody, just wanting to be acquainted with what it says. All right. So therefore, I changed the title to Invariant Maximality slash Derivations for chapter two. The rest of the chapters are stated to be the same. Okay, and now um, uh, so there's been some change in there's now definitely a change in the table of contents. So here's 2, 1, 2, 2, 2, 3 are absolutely unchanged, and the content. So we really start the thing with 4 when we bring in invariance. And I say invariant maximality on the Q2 to the K. Uh, so the most trivial notion of all is shift and shift invariance, but it's totally useless for invariant maximality. It's much too strong. The shift of x is just x plus 1. You just add 1 to all coordinates. And that turns out to be much too active, so to speak. So that in the later chapters where the negative things come in, we'll talk about where those chapters are, sections are. Um, we refute things like the using the shift. You can't use this. Now the pure end shift is the golden one. So this is the one which I'll be explaining to you that's new. And this whole yeah, and this whole section is on cue. And we also have our end shift that we've been talking about for weeks, and n equivalence that we've been talking about for weeks. And I'm just doing it on cue. And the emulators, which I don't emphasize much these days, but is important. This is all on cue. And caution, I don't know that any of these things are independent. But that's fine for the mathematicians because I tell them that because the point here is that all this stuff uses large cardinals. I don't know how to prove them. Well, at least right now, I'm going to look at this one more carefully. But I don't know how to prove them without large cardinals. That's already interesting. And then I say, then I say the proof actually works for the intervals. The same proof works for intervals. And there I do know it's independent. So I do know this is independent because of what I was saying, for the last several weeks, because we were talking about this, right? And then I called it initialization. I now call it simply a consolidation of q to the k and minus n to the k. So this is a third setting. So there is this setting of just the q to the k. Here's the setting of the intervals. And here's the setting. This setting is q to the k, but you cut back down uniformly to the intervals. So it really deserves a separate section. That's the way I want to set it up. Now, it's the ones in here It's the statements in here, which we're all going to give this here. It's the statements in here which are old. I mean, we've been talking about them, not new. It's the statements in here that I use that I prove, because remember, this is a derivation of the chapter. So we might as well prove stronger statements, unless it gets out of hand. You want to prove stronger statements. Um, so that's what we use, the ones in here. But these are considered really important. I now decide that these are important, even though I don't know the status of them. I decided it was worth proving equivalence and understanding of something about the relationships between these statements is worth doing. It's as expected. I can't show that the pure N-shift version implies the N-shift version, but I think I can show the N-shift version and the N-equivalent versions are the same, as well as the emulators, as long as you stay away from the pure N-shift. Yeah. Anyways, that's the tale. Okay. All right, so there are really three settings, and I want to understand each setting separately. I do prove flat out there are plenty of equivalences within this region here that I don't know is independent, but I can still do a lot with it. Um, and there's equivalences between as I already proved in the earlier versions. I already handled um, I already handled that everything in 2.5 and 2.6 are all equivalent. Now that I have the pure N shift, that's not quite true. The pure N shift ones are going to have to be handled separately, and they're probably all equivalent, but they're not equivalent to the other ones, the pure N shift and the and okay, but you can see that I need to do some quite a bit more polishing of this chapter, but it's under control. All right. Dimension reduction was always something that was important to state, that covers in every situation whatsoever, there's dimension reduction. If something's true in dimension 18, it's true in dimension 17. All right. And then this is all these are unchanged from before because we're using this consolidated thing. Uh, Here, consolidated. This is a new word. Okay, we use the consolidate. So this is totally unchanged. I can't remember how much details I had, but I worked out this in great detail in polished finished drafts, polished finished draft form. The positive proofs. Oh yes, uh, there's one little thing I probably need to add. I think I should add, and that is uh, I should probably say something about K and N. N is the interval and K is the dimension. Uh, how the length of the interval affects the size of the large cardinal used. I mean, this was all worked out in a different context, in a slightly different, in a different context in the 2025 book. In the locally maximal invariance. Okay, so we talked about that last time. And then I think we talked about this as well. There's no real change, except there are more statements I have to say are implicitly pi 0, 1. Okay, now all these new statements, and all the statements on Q, no matter what, I can't show that any of them are implicitly pi 0, 1. They're just implied by something implicitly pi 0, 1. That doesn't mean they are actually. So I have to say something about that. There's another notion here uh, that something follows from an implicitly positive one statement. Yeah, so I have to rethink this a little bit. Um, okay, now this I cleaned up, and I had to do a fairly serious effort to clean this up. And let me tell you what I found, because I already stated this last time, that I can't, I that I that there's some basic open cases where I don't know whether they're secured. We'll go over this again. But then I realized, see, I had really wanted to do optimality theory. And I got stuck, and I kept telling you about it, and I kept not, kept erasing it from the and not having it in the next lecture and all that stuff. So I never really stated and proved any optimality theorems. And the reason is I got stuck each time, and I realized why I was stuck. The reason I was stuck was for the same reason that I'm stuck in here, that there's some cases that I don't know are secured. We'll go over what that means. Um, there's some cases in here that I still don't know whether they're secured. I mean, it's basically only one case. There's only one case because they're equivalent up to isomorphism. There's only one case. I should say that actually. Uh, there's only really one case that's open. However, let me tell you what that means. It turns out that the numbers 2 and 3 are important. Um, let me put it this way. I suddenly realized that I'm unable even to this day to determine whether uh, these notions, pure N shift, and N equivalence, are they optimal in dimension 2? Now, everything is optimal in dimension 1. Everything collapses into one thing. Okay, that's nothing. But uh, the question is in dimension 2. So it turns out that I can't figure out yet whether these three things are optimal in dimension 2 um, because it's tied up with the case that I don't understand in here. See? So um, right. Now let me tell you what does happen though. I believe that now that I understand this better, that I can actually show that these things are optimal in dimension 3 and higher. In dimension 3 and higher, these things are optimal. But I haven't had time to state what is the best way to talk about the optimality? What is the right optimality statement? I'm beginning to be convinced. I used to do it with invariants. It gets confusing. You ask for certain invariants to be themselves invariant. It's cute and all that, but I think it's better to talk about quantifier free definability in Q comma less than comma n. Quantifier free definability in Q comma less than comma n is very important. Uh, and I want to say that these notions down here are optimal if you try to do if you try to do the work that any of these do with uh, a quantifier free notion, quantifier free over Q comma less than comma n is a unary predicate. If you try to do that, uh, you'll wind up with these notions being the best, the strongest in the appropriate sense. So that's what this thing should look like. And I've decided that I'm going to treat all these three things fairly. I'm going to, whatever I prove about these, I'm going to prove about these. Uh, so that requires probably some more work. So I'm going to have to do some more work on this. It's going to take a little time. All right, this is the same. This derivation now can be done from the pure N-shift form. The pure N-shift form is equivalent to con SRP because of this last section. This is the old thing. This is the statement that this is the statement that was reversed in the old chapter 4, which is the new chapter 6. Okay, so let's proceed here with some details. Okay, all of this stuff is the book. This chapter doesn't even start till in any serious way till you get to here. See, this is all the stuff that's before we actually do any invariance, just pure maximality. 2.1 is just the introduction. Okay, so this is the beginning of the story right here. And let's see how I reconstituted this. So I talk about the section broadly. In section 241, we introduced the two most basic shifts on Q to the K relevant to current invariant maximality. Only the second one, the pure N shift, is usable. Where usable will mean, I used to have a technical definition for it, but at this point, in the beginning of the book, it's not important. Usable is fine, just an English word. Okay, in section 242, we present the seminal statement of invariant maxima. So this is the thrilling statement. And it's done on Q to the K, and it uses the pure N shift. So this is the reason why I'm doing more work, because of this. It simply requires that the maximal chain be pure N shift invariant. That's it. And it's impossible to require that the maximal chain be shift invariant, which would be even simpler. But we see that kind of thing in section 20, in the end, towards the end of the chapter. We prove a strong form of this seminal statement in section 212 using the large cardinals. At the time of this writing, we don't know whether this seminal statement is proven in ZFC or even in much weaker systems. However, we do know that various strong forms of this seminal statement require large cardinal hypotheses to prove. And that reversal is linked to the rest of the book in section 2.19. All right, so in section 243, we introduce the more powerful pure N shift and equivalent invariance to give stronger forms of the seminal statement, which we also prove in SRP plus. Well, do I want to? All right. All right, let me not worry about it. This is just pure expositional. Whether I want to introduce whether I want to use a less technical system or a more technical system here in the discussion, this is not, we have to worry about this. However, we still don't know these statements are proven in ZFC or much weaker systems. In section 244, we switch from maximal chains and order invariant relations to emulators of finite sets and use the same notions of invariance. And at some point, I can't remember. Yeah, not in this chapter. We actually show that the uh, whether you use emulators or maximal chains, it's the same. It's equivalent, provided you use the same invariance notion. There are three invariance notions. Yeah. All right. So more specifically, here we go with the thrilling statement. The most basic notion of shift invariant of shift relevant to invariant maximalities is as follows. The shift of x is x plus 1. That's thrilling. The shift of x is x plus 1. In other words, you add 1 to all the coordinates. And to be shift invariant means x is an S if and only if x plus 1 is an S. This is utterly useless. It's far too strong. One can refute that you can use this for what we want to do. Um, uh, in other words, can you always get a maximal chain that's shift invariant, right? The answer is no. Okay. So the lie is that we started with this shift invariance and we weakened it to pure end shift invariance, which you know is a big lie because it was a much more convoluted discovery of of how to, of much more convoluted story about how I came up with this. All right, so the pure end shift, here it is. The pure end shift of x in q to the k is the result of adding 1 to all non-negative coordinates, provided that they're all integers, x otherwise. And if you recall the 2025 book, this is what's going on when I was fooling around with -1, 0, right open, 0 divided by n, dot, 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 n divided by n. If you multiply through by n, this is what's going on. If I were doing it on intervals, Yeah. So there are uh, uh, two expositional insights here. One is put it on Q and then talk about intervals later. And the other one is to use the pure end shift. Okay. So we write P, little p, end shift of x. And S is pure end shift invariant if and only if for all x in q to the k, x is an S if and only if p end shift of x is an S. Nice and simple, clear. I might even give an example of two pure shifts in 3 dimensions. One is going to be the identity because there's the number a half is in there. And the other is just going to be adding 1 to the positive integers. All the coordinates are positive integers or non-negative integers. That they just added 1. I think that I will add that. Okay. And then the seminal statement on the Q to the K says this. OIR means order invariant relation. Max means we're taking the maximal chains, CH. And then the invariance is P and shift I. The I means invariance. And we're using Q to the K as the spaces. Every order invariant relation on every Q to the K has a pure end shift invariant maximal chain. So that's my best statement, although I don't know it's independent yet. Maybe I'm still going to do something about this, but anyways, here it is. All right, and then the pure end shift once again, you add 1 to all the non-negative coordinates, provided that they're all integers, otherwise you do nothing. That's the definition. All right, now we prove this statement using large cardinals, and then I go on to strengthen it in two natural ways. I use the end shift, which we've been talking about, and n equivalence. So with the end shift, we don't use x plus 1. Instead, we only add 1 to some of the coordinates of x. Well, that was already true. That was already true before. I don't know that I should. Uh, I'm going to change this to mean something like this. With the end shift, we add 1 more often, or often is probably the wrong word. Then in more cases, we add 1 more in more cases, blah blah blah, than we do in the. I might say something about how the end shift compares with a pure end shift. You know, something about it. I don't know, but something not as silly as this. All right, so now we define the end shift. I decided that given the fact that the pure end shift is being uh, emphasized. Um, I think I feel better about using the entail, which of course is very important for all kinds of later developments. The entail of X consists of the coordinates xi for which every xj greater than or equal to xi lies in N. And then the N shift is you just add one to all coordinates in the entail. That's written this way. The N shift invariant means for all x and q to the k, x is an S if and only if n of x, n shift of x is an S. Just 1 second here. Now, what did I want to do? First of all, I want to, just a second here. Doing some typesetting here. Now, what was I bothered by? N shift is obtained by adding one to all coordinates in the entail of x. Here, that if and only if, that's what I was worried about. Should be. Okay. Here are some illustrative examples of N shifts. So this is old stuff we talked about before. Now, N equivalence, I've been defined it slightly differently. If and only if X and Y are order equivalent and the entails of X and Y occupy the same positions. There are many ways to say it. Why not this? Remember, now that I have the pure N shift, it's so nice. I don't have to baby everybody about these other two notions. You know, they can actually have to use their brain. Okay. All right. So we have now the other two Lee statements. Every order invariant relation on every Q to the K has an N shift invariant maximal chain, and it also has an N equivalent invariant maximal chain. The equivalence, the invariance is actually defined explicitly. That's another change. Yeah, actually give it. I prefer that for some reasons, you'll see. All right. Oh, and then we want to prove that this one's the strongest one of the ones. This one implies this one implies this one. And the way you do that is over here. X and P N shift X are and N shift X, they're all N equivalent. Yeah, they're all N equivalent. And if the P shift is not X, in other words, you're doing something. If you're doing something, then what you do with the pure N shift is actually the N shift. Yeah. So this suggests a notion of stronger. This is a trivially stronger invariance because of that. All right. Now, N equivalent invariance implies N shift invariance implies pure N shift invariance easily from here. And then from here, you get this. Okay. And then we have emulators. Emulators are an important alternative. No, we haven't talked about them for a while, but they're nothing new. you have a finite set, and every element of S squared is order equivalent to an element of E squared. The only thing new here, whoops, is we're doing it on Q instead of the intervals. So this needs to be changed. Okay. Every finite subset of every Q to the K has a purely n-shift invariant maximal emulator. Every finite subset of every Q to the K has an n-shift invariant maximal emulator. And also for this one. Yeah. And then these are obviously for the exact same reason these descend. Okay, now we simply lift everything to intervals separately. I think this is just the very best way of doing this, expositionally. Let's say, okay, so we have all these statements on Q. We're not quite sure whether they're independent. The only proofs we have are we're using large cardinals. So now we put everything on the intervals. We say, wait a minute, the same proof works for intervals. And actually, we see later that the same proof works uniformly for intervals, even stronger. So let's look at this on intervals. And now we know it's independent. All right, so a big point here is that the intervals are not closed under the shift, so we have to be a little bit careful what we're talking about. So sometimes we use the interval minus n to n minus 1 to the k because we want to add 1 and stay in the space. So I define shift invariance for subsets of minus n to the k to mean this. And for pure n-shift invariance, if and only if for every x in here, x is an s if and only this. So I already built into the definition of invariance, subtracting 1 off the right endpoint. If you don't do this, this is nonsense. So you got to do that. All right, S is n-shift invariant if and only for all x in here, x. This is this. Now, n equivalent invariance, by the way, this is invariance with respect to equivalence relation. This one doesn't care that it's an interval. The plus 1 doesn't really come up. S is n equivalent invariance if and only if for all n equivalent x and y in the space, x is an S if and only if y is an S. And then we have the 6 statements. We have our 6 statements. Yeah, I should probably emphasize that there are 6 statements on Q and 6 statements on the intervals. Yeah, 6. I just listed the last, the 3 in 2 different parts of those sections. I should probably put them all together at one point, maybe each display them separately, but also put them together so that you know that there are 6 statements here. Okay. And then the final one is the consolidated form. The consolidated form. These combine invariant maximality, combine the intervals and the Q to the K. So let's talk about, now this is not new. I talked about this last time, but you can just see how it flows. See, and now I write this thing with 3 of these. which is nice expositionally. So it's every order invariant relation has an S whose restrictions are invariant maximal chains. And in the previous versions, I never did that for emulators, but you can do it for emulators because whether you're using emulators or maximal chains is an independent choice of cardinality too. So you might as well, whatever you say here, you might as well say for emulators. So yeah, for emulators, we're going to have these three versions. Yeah, so you can work out some large number of statements that are going to be equivalent. Actually, we only have certain equivalences, right? Of course. And so this has to be rewritten with stuff I've already written. And then now this is the stuff that doesn't change because now we are talking about the consolidated form, the consolidated form. So we didn't make any changes there. And I polished this up when I used the large cardinals. So far, this is just omega 1. Yeah, we're into the large cardinal case. Anyways, we don't really need to talk about this. Oh, no. All that was dimension 2. I'm sorry. All that was dimension 2 using omega 1. And now we have a longer section. By the way, that's not my notation anymore. Yeah. Okay. All right. So this is all this stuff about proving it from a large cardinal. Okay, we're done with that remark. Okay. Now formalizations and implicitly positive one is the same as we discussed, except there are more statements that I have to check are implicitly positive one with no new ideas. Just I have to compile them more. Just more to compile. Nothing going on here. Yeah, here. I got more statements to compile. All right, now this was polished up. This is worth talking about. It's now clearer. I use minus NN in the official stuff, minus NN, nice and natural. And I use that, but now we want to talk about any interval. And I might as well do it even more generally. I use extended real number endpoints. Extended real number endpoints. It's convenient to break with the tradition that N and M stand for positive integers, which is what I do with the rest of the book, but just range over non-negative integers here. And then we're looking at the following statement. Every order invariant relation on every j to the k has an n-shift invariant maximal chain where k is fixed. So where j is fixed, j is one of these intervals described up here, where j is fixed, k is not. Okay, and we can do it for this and we can do it for this. actually, I now want to do it, now I want to do it for pure. All right. All right. Okay. J is fixed and K is quantified. And so we define security. J is end shift secured if and only if that holds. So this is a property of J. J is an equivalent secured if and only if that. Now, you know that I want J is pure end shifts. See, this is how this grew. Uh, all right, I want two of these. Forgive me for you know what I'm talking about. I want three different ones here. I'm not going to type this out for you. Uh, well, we have some patterns here. Okay, so here is the. It took me a while to actually state this properly, but I managed to do it. Um, yeah, I haven't taken pure invariance into account in working on these intervals, um, but it shouldn't be a much. Shouldn't change things much. All right. So what are the intervals that I don't understand? And I mentioned that last time. These are the intervals that properly contain n to n plus 2 closed and are contained in n to n plus 3 open. And they're basically all they're isomorphic for our purposes, they're isomorphic. So there's really one case. Now, already in previous sections, we already know that these are secured. Minus n, minus 1 infinity, minus infinity n right closed, and Q itself. And that comes out of all that work involved to show the equivalence of lots of the statements. Most of the statements are equivalent to each other, that we're fooling around with. And you have to get these long chains. The way to do it is get these long chains of equivalences where they start off and they end where they start. Or the last implication is from the last one to the first one. Uh, so this is the key lemma that is very helpful in this. If I have two intervals in an order preserving bijection, then I know that maximal chains are preserved. Maximal chains are preserved, but I got to show that invariance is preserved. That's what I want. Well, so the hypothesis is that for all x less than or equal to some non-negative integer inside the first interval, J1, x is in n if and only if h of x is in n. Yeah. I mean, this is just a combinatorial property of intervals that I'm talking about. Order preservation between intervals is just dependent on the left endpoint situation and the right endpoint situation properly defined. So I divided it into two cases. What happens when the minimum element of J is a non-negative integer? The minimal element is a non-negative integer. That must mean we have left brackets and something. right? So I handle this case first, but I don't completely finish. First of all, if it's short, this is quite short, right? If the interval is short, then it's secured. In other words, I can do my statements on it. All right. Uh, However, if it's long, really long, and remember, we're only talking about the left endpoint is closed, and the non-negative integer n. If it's long like this, then it's not secured. And if it's somewhat long, if it ends in a positive integer, then it's also bad. And then it's bad if it contains the number n plus 3, no matter what. If it contains the number n plus 3, then I know it's bad. Okay. As the time we're just running, we don't know the status of these days. Okay, so that's the first case. And the second case is when the minimum is just not a non-negative integer, and then I can solve everything. And the way I do it, it's actually easy. The way I do it is I combined, I took this lemma and I combined it with this here. I combined it with this, and I used this lemma. Okay. So here's the characterization. All intervals are secured with the following possible exceptions. Possible exceptions. N plus 2, and n plus 3 contained in J contained in n to the infinity are certain exceptions, are guaranteed known exceptions. None of these are n-shift secured. And these in here are possible exceptions. These J's are all secured or all not secured. Yeah. I think, wait a minute. Yeah, let me think about that. I think that's right. All right. So the optimality I want to use, I want to be very particular about how I state the maximality. And I think I'm going to use the notion of quantifier, as I said earlier, quantifier free definable in Q less than N. That you basically, as long as you stay in there, if you try to do something like the pure N shift and the N shift and an equivalence, then they are the best. These three are the best. And then finally, 219, that's something I think we even went over some. That doesn't need any more work. That from the pure N shift invariance statement, you can immediately get this OISD statement. Okay, so that's the current state of affairs, and I obviously need another week. Again, I'm hoping that next week is the last week on this chapter, but I failed in the past to follow that, but we'll try. Thank you. I'm done.